Well, two should have. There's just a lot of like.
On this side.
Okay, so let's go over the homework. We've got f of x equals x squared minus 16. And we're asked to find the intervals on which f is increasing or decreasing. Okay, so the first derivative test tells us that we should be looking at the derivative. Okay, so listen, this is what makes this hard is understanding the connection. Once we get that connection and understand why we're looking at the derivative and why we're looking at the zeros, it helps, right? So this is a function that we should recognize, right? This is quadratic. Okay, x squared minus 16. So I've got a parabola going down like this, right? That's what my f of x looks like. Okay, I know, right, that I have a minimum point down here, right? I know that for a fact. But if I look at that minimum point, right, because it's a minimum, because it's changing from, in this case, decreasing to increasing, right, my slopes of my tangent lines. If we look at the slope of the tangent line, right, my slope of the tangent lines are all negative over here, and then we change to positive. At this very point, the slope of the tangent line is what? Zero. So what we're doing, anytime we have a minimum or a maximum, the slope of the tangent line will be zero. So what we have to do is find the derivative. The derivative, remember, the derivative tells us several things. First, it tells us the instantaneous rate of change, right? It tells us the slope of the tangent line. It tells us the slope at that point. Okay, so the slope of the tangent line is zero. So I'm going to look at the derivative because the derivative tells me the slope of the tangent line. In this case, it's 2x. In order to find the maximum or the minimum, I need to find where that slope is equal to zero. Is this making sense? Okay, making those connections, right? So in this case, the slope is equal to zero at x equals 0. Now what I have to do is find out whether, in fact, that is a relative extrema. Because remember yesterday, or whenever we met before, we saw an example like this, where we do have a point where my slope might be 0, but it actually does not change direction. So it doesn't have a relative extrema or relative minimum or maximum. So what I have to do now is check to see if I have a relative minimum or maximum at this point. So here we have x equals 0. So we just make ourselves a little table. Okay, to the left of 0, so maybe at x equals -1, what's happening with f prime? It's going to be negative because 2 times -1 is negative. I don't really even care what the actual value is. I just care that it's negative. The slopes are negative when we're less than 0, which means f of x is decreasing there, which we know because we were familiar with this function. To the right of 0, at x equals +1, I get a positive result for my slope, which means f of x is increasing. Since I go from decreasing to increasing, then I know I have a relative minimum at that point. So I have a relative minimum at x equals 0, right? It is decreasing on the interval, right? Everything less than 0. So from -infinity to 0. And it's increasing from 0 to +infinity. Okay. Now, some people prefer, instead of setting up your table like this, they prefer setting it up with the intervals. So my critical point, right, this is my critical point, is x equals 0. So I'm going to set my intervals up to be x is less than 0, and then here we're going to do x is greater than 0. Some people prefer to set their table up like that because it makes it easier to translate to that. Yes.
So you plug in like the x equals -1 into like the derivative?
Yes.
Okay, that's
Okay. I expect that the biggest problem that you're going to have with these is actually solving for 0, because that's going to involve things like factoring and stuff. All right. Okay, let's look at number 2. We have f of x equals x cubed plus 4x. We're trying to find where it's increasing or decreasing, okay, which means we're trying to find the slope of the tangents, right? So we're going to do f prime of x. That equals 3x squared plus 4. Is that right? Okay. So setting that equal to 0, I get, right, -4. So x squared equals -4/3. So I know right away that I do not have any real zeros here. So what does that mean? Well, this is an imaginary number, right? So how do I figure out the increasing and decreasing intervals? Okay, it's another, if there's no real zeros there, which that means that the slope of the tangent line is not changing direction, right? In order for the slope to be changing directions, it has to be crossing the x-axis somewhere. If it's going from negative to positive or from positive to negative, it has to be crossing the x-axis somewhere. So that means that the slope of the tangent line is not crossing the x-axis, so it's not changing directions. Yes. Lauren.
never mind.
Okay. So, yep, Faith.
Can it cross like the x-axis but like not change directions? Like it was like.
It can, yes. But this indicates that it's not crossing the x-axis. Right? So if I were graphing this, because I have x squared equals a negative number, right? This is a parabola that's doing something like this, one of those, right? It's not actually crossing the x-axis. Yes, Caitlin.
If you change directions underneath it, it just won't just be like positive. Like it's still going decreasing and increasing.
Okay, so this is f prime that we're looking at, right? So let's go back up to this example, this curve that we're familiar with, right? If I were graphing f prime, right? Everything to the left of 0 is negative. So everything down here is negative. Everything to the right of 0 is positive. That means at some point it's crossing the axis. So this is the graph of f prime that we're looking at, okay? So down here, the graph of f prime tells me that it's never actually crossing the x-axis. See, this example, the graph of f prime was linear, right? This example, the graph of f prime is quadratic. So it's doing either that or this. I don't know where it is on the graph, but it's not crossing the x-axis. This is telling me that f prime never changes direction.
So changing direction just means going across the axis.
Right.
Because I think changing direction is one's going up and then one's going down. So like even if it's a parabola, you're still changing direction. So it's not linear. Linear is the only one that when it doesn't really change.
Okay, so you're right, but you're confusing f and f prime, right? So since, or maybe I confused it when I said it, I'm not sure. But this is telling me that f prime is never crossing the x-axis, which means f of x never changes direction from increasing to decreasing.
Oh,
Okay? Which means f of x is either always increasing or always decreasing. Let me say it again. Since f prime does not have any real zeros, since there are no real zeros for f prime, the tangent, the slope of the tangent never changes. It's either always negative or always positive. Does that make sense? So we have to just pick a number. I'll pick 1 to figure out whether it's always positive or always negative. So if x equals 1, then f prime of x is positive. Okay. Now that we figured that out, let's actually look at f prime. What do we notice about f prime? It's 3x squared. What do we know when we square a number? It's always positive. When we square a number, it's always positive. So f prime will always be positive, which means what's happening with f of x? It's always increasing. Yes, it's always increasing. Okay. Now we're familiar with this function, right? Our leading coefficient test, our disco math, this is cubic and it's positive. So the ends are going like this. I don't care what's going on in between. Right? The ends are going like that, right? We know cubic functions. This is one of those examples, right? Here's a cubic function. Does change concavity, but it's always increasing, okay? Okay, number 3. How many of you had trouble with number 3? Yep, okay. We've got f of x equals 2x to the 5th minus 15x to the 4th over 4 plus 5x to the 3rd over 3. Okay, let's take the derivative first before we start messing with this. So f prime of x, that's going to give me 10x to the 4th minus, bringing the 4 in front, my 4's will cancel. So this becomes 15x to the 3rd. Same thing happens with 3. When I bring the 3 in front, my 3's cancel, so plus 5x to the 2nd. Okay. So it's kind of scary looking, but when we take the derivative, simplifies it a little bit. Okay, so now I want to set that equal to 0. So I'm going to factor a 5x squared out. And it gives me 2x squared minus 3x plus 1. Okay, so looking for my critical points, I've got 5x squared equals 0, so x equals 0. And then I've got 2x squared minus 3x plus 1 equals 0. So I'm going to try to factor this. You can simply use a quadratic formula to come up with these values, right? If you can't factor and you don't see how it factors quickly, use your quadratic formula to get your zeros. So let's say 2 and 1. They both have to be negative, so this is going to factor 2x minus 1, x minus 1. So x equals positive 1/2 or positive 1. Okay. Okay. I'm going to set, those are my critical points, right? 0, 1/2, and 1. I'm going to set this up, let's see, lowest number first, 0, 1/2, and 1. Okay.
Bless you. Bless you.
Oh, excuse me, thank you. Okay, f prime of x and f of x. All right, so let me see. I'm going to say x equals -1. Here we'll do x equals 1/4. x equals, excuse me, Oy. X equals 3/4 and x equals 2. Okay, those are my values. And there's my f prime of x. Okay, I'm going to put it in factored form. 5x squared, 2x minus 1, x minus 1. That's my f prime of x. We good? Okay, so when x is -1, I'm going to get a positive times, right? This is going to be negative times negative. Again, I don't care what the actual values are. I just care whether it's positive or negative. So positive times a negative is positive. Okay. Okay, x equals 1/4. That's going to give me a positive. Okay, now 2 times 1/4 will be 1/2 minus 1, so that's going to be negative. And then 1/4 minus 1, that's also negative, which means it's positive. Now, it's not as common to have a situation like this where it stays the same. So I always just kind of go back and just mentally check it to make sure I didn't make a mistake there, right? So I've got 1/4. So that will definitely be positive here. 1/4, that's 1/2 minus 1. So that's definitely negative. And then 1/4 minus 1 is -3/4. So that's definitely negative. Okay. You can also just plug it in your calculator. Okay. All right, 3/4. So I've got a positive, okay, a negative, and a negative again, right? So that's positive. And then 2, we've got positive, positive, positive. Is that true? Is this positive the whole entire way?
When I plugged it into my calculator, the graph didn't work.
That's not what I got. That same natural. Oh, increasing. What? Yeah.
I got that original.
Okay, looking at the behavior. Oh wait, this is cubic. Okay. I guess that's entirely possible. So we're saying that it's increasing the whole time. Well, let's look at that curve because this one I'm not trusting my results. Okay, so this is 2x to the 5th minus 15 over 4 x to the 4th plus 5 over 3 x to the 3rd. Okay, so this is our f of x. So we're going to look at this and see what's happening. Okay, it is definitely always increasing. Okay, it is always increasing. All right. Okay. The only area that I'm questioning would be this little area right here. So if I did a zoom box there, okay, let's see. Let's just take a closer look at this. Oh, it does appear to decrease here. So I'm going to double check my values. It appears to decrease right here, right?
Is that after the positive window?
It appears to be decreasing. So let me just double check my numbers. Let's see, did I take the derivative correctly? 10x to the 5th. Oh, you know what I'm going to do? Let me go back here. Okay, this is my f of x. I'm going to graph the derivative. Right. Oops, what's going on here? Here we go. Okay, so I'm going to do n deriv. And it's with respect to x, and I'm going to put y1 in there. And I'm graphing it for all values of x.
Isn't that the derivative of the derivative?
No, this was the original function in my mind. Okay, so red is the derivative. Okay, so remember, when the derivative is positive, f of x is increasing, right? So here's my graph of the derivative. So I'm going to zoom in on this space between 1 and 2. Because if we look at it, it's clearly positive. Actually, I'm going to zoom in between 0 and 2. It's clearly positive when x is less than 0 and when x is greater than 2, right? So let's just zoom in a little bit there. Thank you. I'll just put it on the table. It's fine. Okay, so I'm just going to zoom in the box in the area that is uncertain. Okay, does everyone understand what we're doing here? Right? So we're just going to zoom in there. Okay, so I can see this is f prime. This is the derivative. We're looking, derivative is positive, 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 stays positive, but I've got this space. It looks like between 1/2 and 1 where it's negative. So I'm going to go back and check my values. Okay, between 1/2 and 1, it looks like it's going negative. So between 1/2 and 1, we've got a positive 3/4. So what I'm going to do is I'm going to, y2 is my derivative, right? So I'm going to go y2, and I'm going to put 3/4 in there. So I'm going to evaluate the derivative at x equals 3/4. Let my calculator do the work for me. And I do get a negative number. So we made a mistake in our arithmetic, okay? So this definitely comes out as a negative number. So we made a mistake. So let's see. 3/4, that's going to be positive. Well, here's my negative right here. Here's my mistake. Right? If I put 3/4 in here, I get, is that right?
No, you get 3/2.
Yeah.
That's why.
I get 3/4. I get 6.
Which is 1/2. 1 and 1/2.
Which means it's positive.
So yeah, so then it's a positive times a negative times a positive, which is why it's negative.
Yeah, positive, negative.
It's going to be negative right here. It's going to be negative there. There's one mistake. Positive, positive, negative. Okay. So this was a mistake. So what I would recommend, okay. So first off, it just felt wrong. Okay, but you don't have those feelings yet. Okay, it felt wrong to me. So you're like, well, how would we know, right? So what I would recommend, put your derivative in there. Put your derivative in the calculator. Even if you don't do it like I did in y2, here's my derivative right here. Put it in your calculator and then evaluate the points using that. Okay, so 5x squared is 2x minus 1. Put that in your calculator. So based on that, that's matching our graph. It is decreasing between 1/2 and 1. Okay.
Mister, can you go back to your calculator for just 1 second?
Yeah. Okay. Everybody understand how we used our calculator to help us check it and understand it? Okay, the understanding that connection between f of x and f prime of x. Okay. Grace, you look like you're stressed.
Oh, I'm fine.
You're fine?
Yeah, I just had water in my mouth.
Oh, okay. Okay. Questions? All right.
So for the intervals, you would just write 0 to 1/2 increasing, 1/2 to 1 decreasing?
Yeah, so when I put it in intervals, I'm going to say it's increasing from negative infinity to 0, unioned with 0 to 1/2. Oh, I'm sorry, we could. Yeah. Thank you. 1/2. Unioned with 1 to infinity, right? And then it's decreasing from 1/2 to 1. Okay. Okay, let's see. Number 4, trig. We love trig.
Yeah.
Woo! All right, f of x equals 3 cosine 3x, and we're going from negative pi to pi. Okay. All right, let's take the derivative of this, which is not such an easy thing, is it? Yeah, we got to do outside, inside. All right, so outside is the cosine. So we've got negative 3 sine 3x times 3x, so times 3. So we get negative 9 sine 3x. Now this is just, it's kind of nasty, right? We have to solve this trigonometric equation. Who remembers how to do that? So we know negative 9 does not equal 0. So that's not an issue. Sine 3x equals 0. Now, where is a sine function equal to 0? At pi.
And at 2 pi.
So negative pi to pi, right? So that's going like this, right? So not at 2 pi, because 2 pi is not in this interval. It's the same spot, but what else do we call that spot? 0. So it's at pi, pi and 0. And by the way, pi and negative pi are the same spot, right? Pi and 0.
Can you repeat that all again? What point were you looking for? 3?
This is where sine is equal to 0.
The critical points.
Okay, this is where sine is equal to 0. Now we have to figure out what those are. Well, this is pi. It's also negative pi. This is 0 or 2 pi. Well, 2 pi is not part of the domain. So we're going to list it as 0 instead of 2 pi. Okay. All right, that's where sine is equal to 0. So that's where, how do I do this now? How do I solve this?
Times 3.
So this is where 3x equals pi or 0. So that means x is equal to pi over 3 or 0. What about that negative pi thing?
It doesn't matter. It's the same thing as
You can do
pi.
plus.
So it is the same thing as pi, right? And so up till now, I've been like, okay, it's the same thing as pi. I'm not worried about it. But when we consider the fact that we are then dividing by 3, right? So if 3x is equal to negative pi, then x is equal to negative pi over 3. Is negative pi over 3 the same thing as pi over 3?
No.
No, so I better include that negative pi over 3.
Well, where's the negative coming from?
The original.
The original domain here.
Because negative pi and pi are the same exact spot.
Right. So initially we were like, oh, don't worry about it. I don't have to worry about that negative pi because they're the same spot. Negative pi ends up at the same spot as pi.
The negative just means you go back.
Yes. So negative, I got to this spot, right? I can get to that spot by going pi, which would be this way, or by going negative pi, which is this way. I can get to that same spot. And when we're just talking about pi and negative pi, they're the same. But because this is a 3x, I do have to include both of them because pi over 3 is right here. Negative pi over 3 is down here. So we're definitely talking about different points. Okay. Okay, so now, let's change these to degrees because it's easier. We think better in degrees, right? Pi over 3 is 60 degrees. Negative pi over 3 is 300 degrees. Okay. So let's go ahead and put that in there. Let's say 0, 60, 300. Okay. This is a tough one because of the trig. Okay. So we're looking at f prime of x. And f prime of x is negative sine 3x. Oops, didn't mean to do that. Come on. Come back. There we go. Okay. So when x is less than 0, so less than 0, my domain is going from negative pi to pi. So my domain is going from negative 180 degrees to 180 degrees. So if I want to talk about less than 0, what type of value could I pick? Okay, negative 30, negative 60, anything like that, right? All right, negative 30. So let's think about what's happening here. Negative 30 is going to be somebody somewhere down there. What are the y values? Sine is the y values, right? So y positive or negative? Negative. So I get a negative value here. Doesn't matter that I'm multiplying it by 3, or does it?
It doesn't because it's still going to be negatives.
What am I multiplying by 3? The negative 30. What's 3 times negative 30? Negative 90? Okay. What if
Oh, because then you're going the other way, so then if it goes.
what if we had chosen negative 70?
Then it would be a positive.
What's negative 70 times 3?
Negative 210.
Negative 210. And where's negative 210?
It's above the x-axis.
Yeah, it's up here somewhere, right? Which means it's positive. So then I'd have a positive times a negative. So this is a really weird problem. Let's put this in our calculator, okay? Because this is a really weird one. Okay, let me just ask you this. Why I need somebody to explain to me why it's a weird one. Why am I
Because you're working like the circle.
Come on. There we go.
Like where you set it too.
So yeah, so my x can be less than 0, but it seems like my x being less than 0 could potentially change.
And that could also, if you think about it, for the bigger numbers you can too, because then it can do multiple.
Okay. Let's
Even the first question.
let's do this, right? So okay, let's do this. This negative pi to pi, this refers to my x values, right? So if x is between negative pi and pi, what would 3x be between?
Negative 3 pi.
Negative 3 pi and 3 pi. Does that change anything for me?
Yeah, it does. Because that means you can do multiple loops because 2 pi is the full.
Okay, so let's put this in our calculator. Let's see what's happening, okay? So I've got 3 cosine 3x, okay? And first off, I need to change this to a radian mode. Okay, now let's adjust our window. So I've got 3 cosine 3x. So how am I going to adjust my window? What should the window values go from?
Negative 3 pi to 3 pi.
Yeah, I think so. Negative 3 pi to 3 pi. Okay. So let's see. Negative 3 pi to 3 pi. And let's go increments of pi over 2 so that we know what each mark represents. Okay.
This is just so like extra.
This is a hard one. I'm not kidding you. This is a hard one.
How did you choose your x
Definitely not
now?
easy calculus.
I just did pi over 2. Pi to, well, I want to pick values so that when I'm looking at the graph, I know what each mark represents. So I want to pick easy ones, right? All right, so graphing, okay, here we go. Oops,
Yeah, no,
I don't want the tree. Hold on a second.
He said never mind.
I saw that graph and I'm like, oh Lord.
Okay, here's our cosine graph. This is going from negative 3 pi to 3 pi, right? Each one of my black marks is representing pi over 2, right? Let's make it a little easier. Let's make each mark represent pi, okay? Each mark is going to represent pi instead of pi over 2, okay? So pi, 2 pi, 3 pi. Pi, 2 pi. Okay, so this is what it is normally. Oops. 0 to 2 pi, this is what you're used to looking at. 0 to 2 pi. That's 0 to 2 pi, that's your cosine 3x, right? If it was just cosine x, I'll make it even more familiar looking. There's your cosine x. Does that look familiar?
Yeah, it's very familiar.
Okay. Cosine 3x, right? Cosine 3x.
Just remove the 3, so then it just looks even more familiar.
There's your cosine 3x, right? So that means I have 3 periods, right? The period, well, not 3 periods, but the period is 3 pi, right? Okay. Okay. So now let's change our window. Okay, so now you're back to being familiar with what it looks like. Let's change our window to the negative 3 pi to 3 pi. Now we're going to get a whole bunch of them, right? So there we go. Okay. So the reason that this problem is so difficult when we look at it, right? Look at all the, right? We're increasing. That's why it's so difficult, right? We've got all these spots that we have to check for the increasing and the decreasing. We've got how many intervals for increasing? 1, 2, 18, 3, 4, 5, 6, 7, 8, 9 intervals where it's increasing and 9 intervals where it's decreasing over that domain.
I was just saying, that's just in that domain.
Right? So that's why it's so difficult, and that's why we're not going to continue with it. Huh? Yeah, the domain just really. Now, just listen, guys. Okay, listen. Keep your focus. You're doing really good. Right? If this was just x instead of 3x, it would be much easier because now I'm only looking between negative pi and pi, right? So then what's that look like, right? So if this was just x, so not only does it change that, but it changes my window because now I'm just going negative pi to pi, right? There we go. What a difference, right?
So glorious.
Okay. Yes, sir.
So how would you even begin? Like, would this first question? Would this problem be on the AP test? Like this exact problem, the 3 like the
Possibly.
Possibly. How would you do that on your own, or could you not even do that on your own?
It would probably be a calculator. It would probably be a calculator question.
I don't remember them giving that big.
Right.
It's like 57.
Exactly. Yeah.
That will not be on a test for this class, right?
No.
Okay, thank you.
Okay. How much time do we have left?
17 minutes.
Oh, we got plenty of time. Okay, let's look at 5 and 6. Local minimum, local maximum.
No answer. We did not answer it.
We're not going to take the time to do all those because it'll take us forever. Yeah, but as long as we understand it.
So basically,
Yeah. Okay, so we've got f of x equals negative x squared minus x plus 2. Go from negative 4 to 4, all right? So from the local minimum and the local maximum. What do I have to do to find the local minimum and local maximum?
You have to find the x-intercepts of the tangent line.
Okay, so the same thing. I have to find the local minimum is where. Okay, listen. This is very, very important. The local minimum is where f changes from decreasing to increasing. That's our local minimum. The local maximum is what? Increasing to decreasing. So we're doing the same thing that we were doing before. Okay, there's my f of x. Set it equal to 0. So we get x equals negative 1/2. Okay. So
No, because you move the one.
move the 1 over, becomes positive, and then we're dividing. Okay, so negative 1/2. Okay. Okay. F prime of x, f of x. F prime of x, we're going to make it a negative 1. Okay. So when this is negative 1, I get a positive 2 minus 1. So that's positive, which means we are increasing. When x is equal to 0, that's greater than negative 1/2, we get a negative, which means it is decreasing. Okay. So we have a relative maximum at x equals negative 1/2. Okay. We are not finished. We're not finished. This is where the relative maximum occurs. This is not the actual maximum value. Okay, let's look at the graph, right? Because graphs speak a lot of words to us. Oops. Okay, negative x squared minus x plus 2. Okay, we're going to look at this. We're going from negative 4 to 4. Yeah, I don't think it's an issue though, because I'm not graphing angles. Okay, so there's the graph. This is f of x. We already determined that the relative maximum occurs at x equals negative 2, right? Or negative 1/2 rather.
Wait, so this is f of x or f?
Oops, hold on a second. I'm going to make, look,
This is not derivative.
okay, listen. Each mark here represents 1/2. Okay, I put each mark representing 1/2 on the x-axis. So this is f of x that I graphed. This is where my relative maximum occurs. The question says find the local minimum or local maximum. So this is where the local maximum occurs. What is the local maximum?
Oh. So then you have to plug it in.
You have to plug it in. The local or relative, right? Local or relative occurs at x equals negative 1/2, but the local maximum is, right? So we're going to go back to f of x. So we're going to do negative 1/2 squared minus, whoops, that's negative 1/2 plus 2. All right, I'm plugging it back in, f of negative 1/2. I need to figure out what that is. So I'm just going to use my calculator right now to save time. Calculate value, negative 0.5. So I get positive 2.25. 2.25. That is my local maximum. Okay?
So whenever you do those, you're plugging in the f of x. But when you're trying to find the other, you're plugging in the f prime of x.
Yes. I used f prime of x to determine that it occurs at x equals negative 1/2.
Where it increases.
Right. Okay?
Oh, so the local max is just the y value for that? Or is
Yes. The actual. Now, we do have to, okay, in this case, because we know the behavior of the function, it's not an issue. But we should also check these endpoints. Okay? Critical points include the endpoints. So up until now, we haven't been using any endpoints and it just keeps on going and going. So I would have to also check f of -4 and f of 4. Now we know the behavior of a quadratic function. It's going to keep going. Like it's not going to change direction again. But if we wanted to double check that, f of -4 is -10, and then f of 4 is going to be the same thing. -8. Oh, it's because it's not symmetric. Okay. So this is -10. This is, was it positive or negative? Negative, thank you. -18. They are both smaller than 2.25. So I have a relative or local maximum at 2.25. What is my local minimum? What's the lowest point that this curve goes on the interval from -4 to 4? On the interval from -4 to 4, what's the lowest value? -18. It is a local minimum at -18, of -18. Because this is a closed interval, I have to consider those endpoints. Okay, that is the lowest point that that curve has. And we can see that on our calculator, right? At 4, it goes down to negative. I can't even see the rest of the curve here. Let's see. -20.
That would technically be the local,
The absolute and the local.
Yeah.
Yep. We haven't talked about absolute yet. Right? That's the absolute and the local. Okay. 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 Listen, because of time, I'm not going to go over the last one. Okay. Shoot. I am not going to be here Friday, and you can't do what I want you to do because we haven't finished. Daggone it. Okay, listen. I'm going to have to make a video for you to watch on Friday on the second derivative test. We've been working on the first derivative test. Okay, so let me just give you a little heads up. So just give me your full attention for the next few minutes, okay? I have a meeting that I'll be in all day. Okay, so I'll be off campus. Okay. No, it's not a dreadful meeting. It's just a meeting that we need all day for. Okay, so the second derivative test, right? What does the first derivative test tell us?
The tangent line, the minimums, the maximums.
It basically tells us the increasing and the decreasing, right? Yeah. Okay, everybody listen. I need your attention. Lauren, turn around. The first derivative test tells us the increasing and the decreasing, which we use to determine the minimum and the maximums. Okay, and that's really important information. The second derivative test tells us the concavity. The concavity. Right? Concave up looks like that. Concave down looks like this. Okay, so the second derivative test is going to tell us the concavity. And basically, we do the same thing. We set it equal to 0 because when it changes concavity, right, if f of x changes concavity, we have a horizontal tangent. Okay, so the concavity, right, if f double prime of x is less than 0, then f of x, right, we're going 2 back, right, f of x is concave down. If f double prime of x is greater than 0, then f of x is concave up.
Oh, so you just take the
Okay.
prime of the prime to find
The prime of the prime, right. Yes, Gabby.
But can't you already tell that from the first test? Because if it's going to be like changing from increasing
Well, here's an example of a function that continues to increase but changes concavity.
Yeah, because it's above, it's
It
above
starts
the
down
x,
and
but
then
then
Right? Okay. These points, by the way, these points where it changes concavity, the points where it's changing concavity, these are called my inflection points. Okay. All right. So, and again, I'm going to make a video, and I'm going to have to go over this again with you in the video, but I want to at least introduce you to it. Now, we can go directly using the second derivative test, right? Okay. If f double prime is greater than 0, then f has a local minimum at that point. In other words, it's concave up. Where it changes to concave up, it has a local minimum. This is the second derivative test. If it is less than 0, which means it's concave down, f has a local maximum. Yes.
Well, wouldn't like with the graphs you showed before, wouldn't they not have a maximum or a minimum, or is it?
It's a local, not absolute, local, right? So if it's going to change concavity, if it's changing concavity, it technically has a local minimum there, right? So it's local, not absolute. Okay.
absolute is the whole function,
Right. Okay. So this we will do more of this when I actually give you the video. Yeah. Okay. Yes, ma'am.
the double derivative test.
Because it's the second derivative test.
You're taking the second derivative.
Yeah, the first derivative, the second derivative.
Okay, listen, that's an excellent question, and one of the reasons that I don't address that at this point is because it'd be overwhelming, but I'm going to try and answer your question. Okay, so, the second derivative is the derivative of the first derivative.
Yeah.
Okay, so when we look at the first derivative, right, right, so now we have a new function, let's call it g of x, right? And if I do the first derivative test on g of x, which is actually the second derivative test on f of x, okay, I do the first derivative test on g of x, now I can determine the maximum and the minimum, or the increasing and decreasing intervals of f prime, or g of x. Which would be the first derivative. Right.
Oh wait, but then don't you say f of x there?
Yeah,
Right,
but
you
what
still
if
looking
she
at
just,
f.
Yes.
yeah, but she just said she has to make it different.
Yeah.
Yeah, but I thought she said you're finding like the minimum and maximum of f.
He wouldn't take the challenge in cases though.
And then you do the f double prime.
He challenged her to see if she could say that challenge.
Oh, sure.
Yes.
Wait.
You are thinking absolutely correctly, but I just got to put you on hold.
Okay.
Okay.
I don't understand what I'm saying. Like 5 minutes.
But you're so you're sitting there thinking, well, can't we just do the first derivative test to determine the maximum and minimum, right? That's what you're saying, right?
Yeah.
Let me just turn the video off here.